This week 11. So in terms of the taught material, 11 is the second week of pipe flow, so we'll finish that today. 12 is next week, which is open external flows on airfoils, wind turbine blades, etc., drag, terminal velocity of someone dropping through the atmosphere. Very similar to what we're talking about. We end up with a drag coefficient, which defines how much force is put on a body instead of a friction coefficient. So we're interested in the forces put on a body rather than the forces a body puts on the water, as we are in pipe flow, as makes sense. And then 13 is really our last time. That's not till after spring break, fall break, Thanksgiving, which is open channel flows, where flow is driven not by an upstream and downstream pressure, but by an inclination and gravity of just like a block sliding down a plane. Is not a bad analogy. So that's kind of where we are. And so this week we're here. Next week we're online. Week 13 is midterms. No class underpinning that. The first week after Thanksgiving is open channel flows, week 13. And then the final week, there's nothing there either. So that's kind of where we are in terms of the big picture. So we'll talk a little bit about pipe flows today, and obviously the relevance of it is clear from this, but also it's present in much more mundane situations, I guess. I looked at the views I had from last year for these things, and I had people surfing down a 100-foot face of a wave. I think we looked at that already. And so something a little bit different maybe this time. And so this is maybe a bit more mundane. I don't think that pipe flow is particularly exciting because it's not very exciting, because it's kind of routine. But it obviously has big implications. Everything in your house is run that way. If you want to be supplied with hydrocarbons to fuel our lifestyles, then natural gas and crude oil, and in fact gasoline, I think, goes around the country in pipelines. Big concentration, obviously, on the Gulf Coast. All the refineries are on the Cancer Alley on the Mississippi, and then the stuff gets sent around the country from there. Natural gas and oil from the Gulf gets sent northwards. Certainly in western, where this is New York State here, right? I'm trying to work out where the boundaries would be. This is obviously Lake Erie, so this would be Pennsylvania here. The northwestern part of Pennsylvania is a big storage area for natural gas, and it's typically stored in salt caverns. And the idea of salt caverns, and a hand up, what's the question?
I don't think you're plugged in. Your big screen.
Thank you. That was a good question. How long did it take you to get that question out? Was it up? Well, you can shout. I don't take that as being rude if you shout if you can't see anything, for God's sake. Yeah, anyway, fine. So, okay, pipelines explain. So, I mean, you can imagine this. Of course, the other ultimate pipeline, of course, is in your body, right? Capillaries and arteries and veins. In terms of taking blood flow around, blood supplies oxygen to your organs to keep you alive, brain and heart most specifically. And it's really very, very similar. The mechanics of that is exactly the same as flow in the pipes that we've looked at. They're even kind of roundish, right? Circular section. And so the idea is to be able to get stuff to where it needs to be used. Population centers are in the northeast. Storage of stuff in the northwestern part of Pennsylvania in salt occurs in salt caverns. And the idea of salt caverns is you just put a borehole down into the ground. It's probably about as good a picture as there. And the idea is you just circulate water, so-called solution mining. When you're making it, you circulate water, you dissolve the brine, you take the brine out, you let it evaporate in lined basins on the surface, sell the salt. And then once you have your cigar-shaped conduits developed, and so these conduits might be 1,000 feet tall, they might be a couple of hundred feet in diameter. then you use that to store either pressurized natural gas or hydrocarbons. In Scandinavia, they actually excavate caverns which are used, they don't have salt, they have granites, they have wonderful but very hard rock, and then they store oil in them, in the subsurface, and they typically have what's called a water curtain, so that outside the cavern, they have water under pressure, so that the only flow is from the high pressure injection points into the cavern, and so if water is flowing into the cavern, oil can't flow out. It's kind of the same principle as nuclear power stations. The domes on nuclear power plants are under pressurized, so that the only flow of air can be into the dome rather than out for obvious reasons. And so these are used, and also I guess in the US, the Strategic Petroleum Reserve in Louisiana is a bunch of these salt caverns in salt domes used to store gasoline, I guess, rather than oil, and then recovered in times when prices are high, national emergency, etc. And so I guess these are kinds of pipes as well. I guess there's not much resistance, as we know, in something that would be 100 feet wide versus something that might be 4 inches in diameter, 8 inches, 12 inches in diameter, typically for these well bores. So that's kind of an exposition of why we might be interested in pipes for flow. So today, if we talk, we're not going to kill it off, but we're going to talk in some detail about some of this. And if you can still see it, what we'll talk about are these things. So I really want to spend most of the time, and I think most of the important stuff to do today is to go through these examples of type 1, which we kind of went through last time, type 2, and type 3 flows, because the way we solve them is different. These are the easiest ones, and it gets increasingly more difficult to do as we go down. But also just maybe talk about, I think the only important one of these is talking about non-circular sections, and I guess the examples. So that's our plan. So these are the two things probably we'll talk about today. And so, do I want to really introduce it? Do you need to see it again? Actually, it never hurts, right? Do you need to see it again? Do you need to see Bernoulli's equation again? No? Oh, God. Well, that'll save us some time. Well, I will make the point. It just occurred to me. So you know from Bernoulli that you can do this behavior for a reservoir between upstream and downstream. So we've done this. So I won't write Bernoulli, but I will write the important features to come out of it. Because there is I always think there's kind of a message with everything I say, but perhaps you don't believe that, of course. Yeah. Sorry? It's a hint. Yeah, it's a hint. Yes. Oh yeah, could be. No, maybe. There is a question like this on the test if that's what you're talking about. Of course, you should want this for your own knowledge, not because it might occur somewhere else. But the bottom line is, if you remember, the important features of this would be the only terms that are going to matter in this are if you write the equations between these two locations, between upstream and downstream. The only things that matter are going to be Z1 minus Z2 from the other side, right? If you have Bernoulli in your mind, not Bernoulli equation, but the loss equation, plus HP equals, so if this is the same diameter, so this velocity is 0, this velocity is 0, this velocity is not 0. And so this is, if we do it only in terms of major losses, then this is the deal, right? And the only losses that occur, obviously no loss occurs in this system getting here, and losses occur here, and no losses occur in this system going here, because the velocities are 0, the pressure is 0 because it's atmospheric. And so this is the equation that governs that behavior. And I guess relevant, if you remember when we talked about the sprinkler system, right? We said you can take a sprinkler, or the vane system for that matter. You take a sprinkler, you hold it static, that generates the maximum force, the torque that you have to resist. And so if you hold it static, its velocity of the control volume is 0 by definition. If you let it go, then it will move with the velocity of the squirting water at equilibrium, but you're applying no force to it, so the force is 0 also. And so for the sprinkler, I guess, if I draw it like that, with the water coming out at some velocity w, then we know that the control volume has to be going at some velocity vcs. And so we drew this diagram. And this diagram was velocity of the control surface and I guess the torque. Torque would be going in this direction, right? T equals force times radius. Then we said that the two conditions that we applied, one is that you hold it static, so it's going at 0 velocity. The torque on that is a maximum. And if you have it going around at the maximum velocity, then by letting it go, then the torque is 0 and the velocity is a maximum. And so we made the point that the work is equal to the torque times the velocity of the control surface, a force times the length multiplied by, actually not control surface. It was the angular rotation, right? Because angular rotation is units 1 over seconds. This is force times lever arm. So this is Newton meters per second, joules. And so if you plot the work as a function of this, by definition at this point here, the torque is a maximum, but the velocity is 0. And so this has to be 0. If we look at this point here, then the velocity is a maximum, but by definition the force is 0. And you saw this curve before, that somewhere in here it has a curve. And you could work out that curve as well. But this is the maximum work you're getting out of the system, somewhere apart between these behaviors. And so you could think about this as this system as well. So you didn't want me to write Bernoulli, but I will write that the work divided by density, flow rate, and gravity is equal to the head, right? The pump head. And so we could rewrite that as being equal to the work is equal to the volumetric flow rate, mass flow rate, I guess, right? This would be what we've called, not divided by, but this would be m dot times g. And so, and multiplied by hb, pump head. And so if you think about it, this flow through here, if you try to solve this problem using Bernoulli, where the pump head and the friction losses are 0, you can't get it to balance, because you can't justify the fact, if you have no resistance to flow, that you'd have an upstream which would be different from the downstream. It would just be the same levels by definition. But the mere fact that we have a flow velocity in here that has friction acting against it means that we have this loss, and this loss increases as we have a higher flow velocity. So as we did last time, there's some equilibrium flow velocity that will give us exactly this h sub l that comes in here. But what we could think about, everyone okay, is a diagram a little bit like this, I suppose. What would it be? I'm trying to think exactly what it would be like. It would be like, so let's say if it's laminar. We know that if it's laminar, HL is equal to 64 over Reynolds number, length over diameter, V squared over 2G. It's getting more complicated than I wanted, really. We know that Reynolds number is equal to a velocity, a density, a diameter, a viscosity, L over D, V squared over 2G. And the reason for doing that is that you realize that if this is the case, we lose one of these velocities. And so the head loss is a linear function of velocity. So for laminar only, I guess head loss is proportional to velocity. Turbulent, just to close the circle. Then head loss is proportional to velocity squared, right? Because we don't get this Reynolds number term which has velocity in it. And so the point of mentioning that is that you could think about this is the velocity of flow in the pipe. This velocity here. And if it's a maximum, whatever the equilibrium velocity would be for this system, then it would be this magnitude, which would be equal to HL. And so it's got to lose, as it goes downstream, it's got to lose this, oh, that's wrong, this delta Z. Right? That's this term here. And so this term is delta Z. So I'm dragging a dead body in here. Good God. And so the point I was making is that the head loss is a linear function of velocity if it's laminar. And so if you're plotting velocity along the bottom here, then this is always head loss. I'm afraid to look. What's the noise? Underneath? Are they excavating underneath us? And so this would be equal to the pump head. And so the only way that you can stop it from flowing at this equilibrium velocity is you can slow it down, and you do that by putting a pump in here, and that pump would give you an amount of work. And so this is a bit like this, right? When you flow the velocity down to zero, I guess if you want to plot energy, so this is the velocity of flow. This is going to be the work that you take out of it, which is going to be equal to this. So, do you want to write it out? So, density times Q is equal to velocity times area times G times HP. And so the relevant terms here to look at are that HP and velocity, it's exactly the same as this. If the velocity is zero, then by definition the work has to be zero because of this term here. If the pump head is equal to zero, then by definition the amount of work you get out of the system is equal to zero. And if pump head and velocity are both non-zero, then that will give you a maximum. And so, in terms of understanding exactly how systems work, that's it's exactly the same as the sprinkler. Hold it static, force is a maximum, velocity is zero, no work, useful work. Let it run, but don't attach anything to couple it to a motor, then you get the maximum velocity, but again, no work. And so these systems have a natural equilibrium velocity, and if you change that velocity by putting something in the middle, it could be a turbine, it could be a mill wheel, I guess, being pushed around, same deal, some mechanism by which you convert velocity into rotational energy and use that attached to an electric motor, then this is the behavior. Okay, so that's it. So that's a diversion. So there is a question in the test that talks about work done and etc. Actually, there's parts of two questions that would impinge on that, but so you have access to that. All right, most of the pipes that we've talked about have been circular section pipes, in which case this friction factor for laminar flow, this coefficient has been 64. And that's probably not going to change very much. But in some systems, such as in ductwork in buildings, for example, the cross-section of the pipe is not a regular section, and indeed it would be kind of prismatic. And we can use an equivalent diameter, which is equal to 4 times the cross-sectional area of the pipe divided by the perimeter of the pipe. And not surprisingly, if you do that on a circular pipe, then 4 times the area is pi d squared times 4. And the perimeter is 2 pi r, which is pi d. And so if you end up taking these out, you end up with 4 times the diameter. And that is because, is that right? Pi d squared upon 4. Pi d squared upon 4 is the area. Pi d is the perimeter multiplied by 4. Not very good, but you can see that the diameter for a circular thing turns out to be the same as the diameter itself. And so it just means that if you have irregular sections, such as this, the terminology I guess we used for moments of area was B and A. So obviously the perimeter for this would be 2 times A plus B, and the area would be AB. And so you could work out exactly what the Reynolds number of that. So if you don't need me to write a Bernoulli for you today, you don't need me to write that. But everything we've done so far, we could do for non-circular section pipes by just substituting the hydraulic diameter, which is this, and substituting the hydraulic diameter written for the relative roughness. And everything else should work out. So in other words, we should be able to use the Moody charts for those, just written in terms of the fact that the Reynolds number on the bottom of these Moody charts should be written in terms of the appropriate hydraulic diameter, and this term here should be the hydraulic diameter. All right? So the other thing is that you can imagine that you might end up with some different coefficients that would at least define behavior for laminar flow in these systems. There must be more than one body, I'm thinking. And so the appropriate magnitudes for those would be things that would make sense. If you have a circular section that has a central core in it, then flow is only within this annulus. Then you can get the magnitudes of these friction factors. It was 64 over Reynolds number, right, before, for a circular section. But now this C is equal to something different. You can imagine that as D1 goes to 0, then the value for this should actually be 64, just by what we've seen. And if it's less than 0, or sorry, if it's more than 0, then it's progressively a number different from that. This upper bound here is if it turns out that if this is actually approaching 1, I guess, hydraulic diameter, if they're approaching each other, then it ends up being like flow between 2 parallel plates, right? You can imagine that if this gap here is very small, then you could unwrap this circle into one parallel plate on the bottom, one parallel plate on the top, and you're just flowing between a slit because you've unwrapped it. It turns out that for flow between 2 parallel plates, just like it is for the analytical solution for flow in a pipe, circular pipe is 64, the analytical solution is 96, turns out, doesn't matter. And so you can imagine that these values, again, for laminar flow, so in other words, we saw it earlier on, right? It was equal to C divided by RE. This value of C that we're talking about here changes based on the geometries. And so you can rationalize, again, for this one, right? As alpha goes to 0, it should be the equivalent for a circular section duct, etc. And I guess as alpha goes to, well, they only go up to 90 here, so anyway. So as it goes up to 90, it's kind of like a quadrant of a circle, but I guess what's different is that instead of being a circle, you've got drag that exists on this surface here and on this surface here as the flow goes into the page, and so you'd expect the friction to be more than for a circular section equivalent. Okay, so that's it. All right, so that's where I wanted to get to. And so I won't write Bernoulli for you, but you see it there. I snuck it in. But we'll make a case that if we want to solve for real problems, we have to do something, and we can rationalize these different types of flow that we solve for. And last time we took care of this type 1 problem. And so all they do is they differ on what we know, what parameters we know. And for the ones that we solved before, we knew the velocity, and we knew the geometry of our piping system, and we wanted to know what the head loss was. What we could do is we could also switch it around to change the thing that we're trying to determine. The next more difficult one would be where we want to solve for the velocity, where we know the geometry of the pipe system, and we know the head loss between upstream and downstream. That's difficult because we don't know the initial velocity to be able to calculate what the friction factor is to be able to calculate the velocity. And so that's the why as we go down here, they get progressively a bit more difficult. And so I won't use this, but I will use this. So this is what we did last time. You will hopefully recognize this. So I wrote something on the top, but I guess I don't know why it got messed up. I could write it again if I wanted to, I suppose. It was it was something, I don't know why it dropped off the top. It was just that the head loss, which is equal to an Euler number, which is a friction factor, is equal to a function of velocity. Actually, I think I had it written as Reynolds number, right? Reynolds number, which is a function of velocity, length over diameter, and relative roughness. That's all that dropped off. And I guess it's not, and really the head loss is equal to friction factor, length over diameter, v squared over 2g. And so just to reintroduce ourselves to our bearings, we made the point that if we have turbulent flow, all of these curves are horizontal, and so the friction factor doesn't vary with Reynolds number. If it's laminar flow, then it follows this kind of behavior, and the friction factor is not a function of roughness at all. It's only a function of Reynolds number. This, because it's not horizontal, must be a function of Reynolds number on the bottom here. This boundary here is for smooth pipes along the bottom as you go in this transition. And these individual friction factors change from a very rough internal boundary to a very smooth internal boundary. And of course, this keeps on going off the chart. I suppose the other thing to notice is that the range of this, since it's a log scale, is not all that big, right? This is 0.1, this is 0.01, so this is just an order of magnitude. So if you're thinking of in a practical sense, I'm not talking about tests now, but in a practical sense, tests you always get given a number because you want to have a single number coming out. But if you're trying to dimension things, then choosing a friction factor that's somewhere in the range of 0.01 to 1 would be a reasonable thing to do, it seems, because it seems to be within the range of important parameters that we're dealing with. Okay. So what I want to do today is just to go through these three different behaviors that we've talked about. And that is type 1 behavior, where is the easiest because we know the velocity, so we can calculate Reynolds number straight away. So if we know that Reynolds number is equal to a velocity, a density, a characteristic dimension, and a viscosity. And I won't probably go slow enough for you to write this down, but it will be recorded, of course. So remember the essence of what we're talking about. Cross-sectional area is constant along a pipe. Therefore, the velocity in and the velocity out have to be the same. If that's the case, and we start off with the big tanks at either side, when the pressures, I guess we could start off with a pipe at either side, and the pressure at the entry and exit would be the pressure difference which would be the same as kind of the elevation difference between the upstream and downstream. I guess it's not drawn here, but we drew it earlier on, so you get this. But the bottom line is we want to be able to calculate what this head loss term is. And so the head loss is a function of the friction factor, length to diameter, and v squared over 2g. Didn't come out well, obviously. And we said that we could do it for some assumed geometry, that if we take a pipe that's 1 centimeter in diameter, 1 meter long, has some roughness, has a head drop between upstream and downstream that we don't know, then we can try and calculate what this head loss term, which would be just the height of the fluid between upstream and downstream, just as we saw, delta Z. And we could do it for both laminar and turbulent behavior. So if we want to make our own exam question, we come up, and that's not a hint of any kind of, that's what has to be done in reality. But we want to know what regime we're in, so we need to know a Reynolds number. We can define a Reynolds number in terms of everything but the velocity that we choose to give to it for this type 1 problem. Diameter we have, viscosity of water, 10 to the minus 3 Pascal seconds, 10 to the 3 kilograms per meter cubed, and so we end up with this being the Reynolds number. For velocities written in meters per second, then this term is in seconds per meter, so they cancel out. So this becomes a non-dimensional term. And we can do the same things we did last time. This is exactly what we did last time. Just to repeat it, we can get the head loss. We choose a velocity that makes sense for us to get laminar flow. 10 to the 4 times 0.1 is 10 to the 3. 10 to the 3 would be this term here, which would give us, whoops. We know that this is 64 divided by 1,000, right? Because of our 64 over Reynolds number term. Then, if this is the case, then what we get out of it is this term here. We could calculate it analytically, or we could just use that this is 0.064 just by reading off the chart, which is exactly the same as this. And it turns out that our head loss is 3.2 millimeters, which divides this pad. So this is meters. If we want to then migrate onto this side of the curve, then we have to choose a different Reynolds number. And so if we choose a Reynolds number which is greater than 2,000, then if we use 1 meter a second times 10 to the 4, the Reynolds number is 10,000, right? If that's the case, then we can read off the Moody chart for 10 to the 4, if I make it bigger. And we could come up with two values, one for a smooth pipe, which would be this, about 0.03, and one for a pipe, which is, I think, a roughness of 1 over 100, which would be roughly this equation here, which would be 0.043, right? Something like that. And so for these two values, so these are the two values that come out of this. So great, because so long as we know we're turbulent, we know we're on the flat parts of these curves, go straight up to hit a flat line, relative flat line, and we end up with these friction factors. And if we throw these in, this is for the pipe, which is the roughness of 1 over 100, hence this term here. We end up with a head loss, which instead of being 3 millimeters, is 200 millimeters, right? 0.2 of a meter. And so 3 millimeters versus 0.2 of a meter. So as we get higher flow rates, probably not surprising that since the resistance is proportional to the velocity squared, then it goes up some. And making the point that between the laminar flow, where the friction factor is equal to, what is it? Friction factor is equal to 0.064, 64 over 1,000, in other words, right, this term here. And for the turbulent flow, when it's equal to 0.042, not very different from each other, the head losses are hugely different, 3 millimeters versus 200 millimeters. And the reason for that is that the head losses for laminar flow is proportional to, turns out being the, well, actually the friction factor is the same, proportional to the velocity squared. We did it with a change in 10 times the velocity. So one velocity was 1 meter a second, or 0.1 meter a second, and the other one was 1 meter a second. So they're a factor of 10 different, but the head losses turn out to be a factor of 10 squared, right? 200 millimeters versus 2 millimeters. It's not 3 millimeters, right? So that's the point. So that's the one thing that we can do. All right. So that's what we did last time. If we choose the type 2 problem, so the type 2 problem, just to remind ourselves, is what we know is the head loss between upstream and downstream. Big tank, downstream tank, head loss would be the same as delta Z. We know the geometry of the pipe. We know it's 0.1 of 1 centimeter. We know it's a meter long, and we know its roughness, so we know that. We want to determine what the flow rate is. And so our solution to that becomes a bit non-standard because we don't necessarily know the system. So what we do know is its diameter. What we do know is its length. We know the head loss that we can apply. We can choose that. And I think we use 1 meter here or something. I'm not quite sure. And what we want to do is work out what the velocity is. So what we can do is we can take our head loss term equation here. Oh, head loss is 0.1 meters, so fine. And so I guess that is between the head losses that well, it's not between it, is it? What were our head losses before? This was 200 millimeters, 0.2 of a meter, and 0.003 millimeters. So this is partway between those. 0.1 is between 0.2 meters and 0, essentially. So it's midway between those. So I guess we know we're somewhere kind of in this transition between the two. And so what we can do is we can write our head loss, where we know the head loss is equal to this, and just rearrange this. Rearrange it in terms of the velocity. And if we do that, we rearrange it in velocity squared. We just divide everything through by the right-hand side, and we get this as a function of v squared. Square root both sides. Not sure what this is going to here. And we end up with this. So the head loss is equal to 0.1 of a meter. G is 10 meters per second squared. Diameter, 1 centimeter. Length, 1 meter. And the friction factor, just choose a number. So in other words, if you assume it's turbulent and the roughness is equal to 1 over 100, then we know that, I guess I drew this diagram here for a reason. Then we know if we assume, not assume, if you're told that the roughness is this, and this is the value, so you're somewhere along here, and if you're somewhere along here, then I think you're there, so you're 0.03246, 0.038. I can't remember what I used, might have just used 0.04, because that's roughly the same, makes life easier. And if you do that, you can almost do that by hand. You end up with reducing them, you end up with square root 0.5. Square root of 0.5 is about 0.7, as I recall. And so the velocity is equal to 0.7. The Reynolds number is equal to 10 to the 4 times velocity, which is equal to 0.7 times 10 to the 4, or 7 times 10 to the 3. And so you can check whether that's true. So if we go back on here, so 0.7 times 10 to the 4 would be, I guess, this green line, which is already there, which would be that the friction factor is really not 0.04, which we used before. It's about 0.046. So if you come back and use that, well, it wasn't quite there. Now you substitute that back into this expression again. The friction factor was this term here. The friction factor becomes this term here. So instead of being 2 divided by 4, which is 0.5, it becomes 2 divided by 4.5. and this is square root of that is 0.66, and the Reynolds number 10 to the 4 times 0.66. If we zoom in on this, what did I? It's basically unchanged, right? So this would be 0.7, 0.6 would be this little red line here. So 0.66 would be going up to this term here. I think this is the roughness thing that we want. This is roughness of 0.01, which is going up here, which means that it would intersect at this value here, and I can't even draw them different from each other. So we've converged. So the point is, the point is that we've converged on a value that satisfies two things. Our Reynolds number is correct to give us the correct friction factor. And so since these two both count for the same value, then we've solved our problem. So the friction factor is not equal to, but is equivalent to the Reynolds number of flow. So since these aren't the same numbers, but are balanced with each other on this Moody chart, the Reynolds number and the friction factor that we pull off are exactly the same. We've reached a solution. And so we haven't had to make an assumption about laminar or turbulent. We just chose an initial value of the friction factor based on the turbulent regime. It's just convenient for us to do that because we know we're on the flat part of this graph. If we end up being on the laminar side, it would work out okay for us as well. I think, do I do it here? Yeah. So in other words, just need to choose a number. So if you know what the roughness of your pipe is, makes it easy because then you can choose this. I guess if you have a smooth pipe, then you just need to choose a number between 0.1 and 0.01, factor of 10. It's quite constricted, and then do the same. And so, yeah, I'm making that point here. So what we've done, if you look at it from 35,000 feet, we've chosen a friction factor based on our, in this case, based on our roughness. We've chosen the first friction factor. We've used that friction factor to calculate initial velocity from HL is equal to friction factor length over diameter V squared over 2G. Rearranged in terms of velocity, right? This term here. And then we've used that velocity we've calculated to calculate the Reynolds number, which is equal to the velocity we've calculated, density, some pipe diameter divided by viscosity. And then we've gone back to check whether that Reynolds number and friction factor match up. If they're not, then we choose a friction factor number 2, we get a velocity number 2, and we get a new Reynolds number. We again check whether 2 represents that. If not, then we do 3, and you hope that you're converging in this, right? We've converged after basically 2 iterations. So that's it. So if smooth, you can also do it by assuming it's laminar, or choosing a number within this range. I guess if it's smooth, then the curve isn't very different. Well, it is a bit different. This is the laminar curve. This is the smooth curve when it's going through this partially turbulent behavior. So I guess you could choose either ones, but you could choose it to solve for laminar. All right. 5 minutes to do type 3. So that's kind of the most problematic in some respects. Oh, actually, it's not the most problematic. I guess type 3 is probably the worst. So here now we've solved for velocity as a function of known geometry of our system and known pressure drop between upstream and downstream. The third one would be where you want to dimension your system. You don't know. You'd like it, obviously, if you want it to be as efficient as possible, you want the biggest diameter because the head loss will be the smallest. But that's not really the complete solution. You'd want to be able to flow at some velocity to get water out of your faucet in the morning under some pressure that you apply to it, which you know. And so how big are the pipes that you put in your house to be able to do that? And so type 3 would attempt to do that. So we could do it in 2 ways. What am I doing here? Yeah, all right, fine. So if you have a smooth pipe, the head loss is if defined, the velocity is defined. The question is, what diameter pipe do you want to use? Well, certainly in this, you can write the Reynolds number in terms of those. And this was before the Reynolds number was equal to velocity times 10 to the 4. Turns out that our velocity is equal to 1. If we assume that the initial diameter, you have to assume an initial diameter, right, for your pipe. There's no way around that. So if you assume as a first guess that it's 10 to the minus 2, we'd be able to get a Reynolds number. If we assume a friction factor of 0.03, I don't know why I did that. Why did I do that? Not sure. We might be more akin to choose a friction factor of 0.064, right? But anyway, go with this. And so if you write this out, you have a friction factor in here, you end up with a head loss being equal to 0.0015 meters, so 15 millimeters in this particular case. You go back with this head loss this is the diameter of the pipe, this is the diameter. So what am I doing here? Obviously, to be able to calculate a Reynolds number, you need to be able to choose a diameter of a pipe. And if you don't have that, then you can't do that necessarily. So what you could do is just choose a random friction factor. 0.03 is between 0.1 and 0.01. I don't know, it's in here. And so I think that's all I've done here. If you use this friction factor, you end up calculating an assumed diameter of your pipe just by rearranging this in terms of those terms. You substitute this diameter, you calculate the Reynolds number, which instead of being 10 to the 4 is now 1.5 times 10 to the 3. And so this would be if you assume this. If you use 1.5 times 10 to the 3, then you can go back to this. Should use a color that we can see. This is 10 to the 3, this is 2, this would be 1.5 times 10 to the 3. Hopefully I chose to use 0.042, something like that. Let's see if I did. 0.04, close enough. This is the number you get out. You go back to the same expression we used. Now we put in the value of the friction factor here. Instead of 0.03, it's 0.04. You end up with a pipe diameter which is 2 millimeters in diameter. Pretty small pipe, probably smaller than reality, but never mind. And so if you now iterate on that by recalculating the friction number and then going back again, you'd find out that you're not moving. You're stuck between these two values because you can't really, the Reynolds numbers for the two parameters that we've used have been so close to each other that they just don't vary very much. And so that's you've reached some convergence between the friction factor and the Reynolds number that you've pulled out of it. The other way to do this is to realize that kind of in this zone, if this has our Reynolds number, this is equal to 1500, Reynolds number 1500. So by definition it's less than 2000. So 1500 by definition is less than 2000. And so we'd expect that it's laminar. So what we could do is we could write this expression for head losses in terms of a friction factor, and this friction factor would be equal to 64 over Reynolds number. And so now we could write it, there's a velocity term that ends up in here, cancels out with this velocity, and we'd be able to solve for it directly. And so if we do that, then we end up with what? This is just that expression for head loss written in terms of d. Ends up being d squared because we end up with a term in d for the Reynolds number, right? This is Reynolds number numerator, Reynolds number denominator. We've got a D here, we've got a D on the left-hand side, so if you get rid of this D, we end up with D squared. And if we square root this whole term to get D, then we end up with this. So 64, viscosity of water, density of water. This is the velocity of 1 meter a second. We've lost this D, if you see. The length of the pipe is 1. The head loss is 1 meter. The velocity is 1 meter per second, which we've chosen. And 2 times gravity is 2 times 9.8, which is 20. And if we go through the calculation for what these are, you end up with 3.2 times 10 to the minus 6 square root, and you end up with 1.8 times 10 to the minus 3. So 1.8 millimeters, 1.78. And so doing it in closed form, we get something. Remember, if you went through the Moody chart way, you'd oscillate between these two values. And so the difference between them is only 0.0005 meters, right? Is 0.5 of a millimeter is the difference between these. And so you'd oscillate between these two values. This you've solved in one fell swoop to get a value that's actually midway between them, right? This would be 1.78 versus 2 and 1.5. So it's the same way of doing it. And I'm not sure what comes before. I don't know what I'm doing here. The Reynolds number, you check the Reynolds number to make sure that it holds, and it must hold, and it gives you this same value. So you've solved it. So that's it. So it's right on the money. So to summarize, just to put it in perspective, we have these 3 different ways of solving for the problems for this single pipe. By far the easiest is where you know what the velocity is, because you can solve. You know exactly what the Reynolds number is, and so you know exactly where on this chart you are, and you can get the friction factor in one step, irrespective of whether you're laminar or turbulent. In the other cases, if you want to solve for velocity, then you have to iterate to be able to solve for it. You'd have to choose an appropriate friction factor from the relative roughness and solve for it. And the more difficult one is where you want to dimension the whole system based on the velocity term. And so defining the amount of volume, flow rate you want to get out of your faucet in the morning, the pressure you get out of the mains going into your house or by your tank if you live on your own well, allows you to be able to determine exactly what the pipe diameter should be. And of course, having a much bigger pipe diameter means that you can always get that flow with whatever head loss you have, but that means you pay more for your piping in the house. So that's an optimization. So that's it for today. And so next time we'll talk some more about pipe flow. I'm not sure what we'll talk about. We'll do some examples, I'm guessing. So we'll do some more examples next time. And those examples will be the ones that are in the notes. So that's it for today. So, okay. We avoided writing down Bernoulli. I'm happy to do it. And so see you on Wednesday, for those who wish to come.